Hello. So last week we've seen the definition of a Lie group and some important families of Lie groups. And we also have seen what a representation of a Lie group means. So what we're going to do this lecture is look at one of the simplest non-trivial Lie groups, which is the SU2, the special unitary group in 2 dimensions, and really look at what kind of representations one can find for this Lie group. In particular, we're going to classify the irreducible representations of SU2. Now, before I delve into this procedure, I want to be a bit more precise about what I mean with a Lie algebra and a representation of Lie algebra, which is the route that we'll take. So we're not going to solve actually for the representations of a Lie group, but for the representations associated with the corresponding Lie algebra. So here's a slightly more mathematical picture of what we're actually doing. So on the top, what we consider is an abstract Lie group. So for us, an abstract Lie group is really just a set which forms an n-dimensional manifold, so little n. And in this set, we have the identity element, and we have some other elements. And the fact that it has a structure of a group is saying that whenever I have two such elements, they combine into a third element, which is really the composition of the elements G and H. Okay, and then formally at the mathematical level, how do you get a Lie algebra associated to this Lie group? Well, you look at the elements in the vicinity of the identity. More particularly, we're looking at the tangent space at the identity element. So the linear combinations of the generators of the Lie algebra, they span the tangent space of the Lie group at the identity, and this is really what I call the Lie algebra. It's naturally a vector space because I can add up tangent vectors, and I can also multiply them by real numbers. Okay, and then I know that if I have this formal Lie algebra element, I can map it back to the Lie group via the exponential mapping. So it's taking some vector here in this tangent space, and it's basically projecting it down onto this curved Lie group. Okay, and as long as you're very close to the identity element, if I want to compose two Lie group elements that are given by, say, the identity plus some element of the Lie algebra, then that just amounts to adding these vectors in the Lie algebra. But if these vectors are not very small, there is an error that you're making. And this error that you're making is really the non-trivial group structure of the Lie group. And at the level of the Lie algebra, this is encoded in a mathematical structure, which is that of the Lie bracket, which associates to a pair of vectors in the Lie algebra another vector. And as soon as you know the structure of this linear bracket, so this is the Lie bracket, then you know all that there is to know about the group multiplication structure in the Lie group side. Okay, now for pretty much all the applications that we physicists are interested in, we're not working on abstract manifolds and abstract vector spaces. We're really dealing with matrices. And when you're dealing with matrices, you're dealing with representations of your abstract Lie group. So recall, a capital N-dimensional representation of a Lie group, so that's really a mapping from your set G to the set of all invertible n by n matrices. So we're assigning to each group element some point in the space of all n by n matrices. And the collection of all these points, it will be some manifold, some continuous hypersurface within all the n by n complex matrices that one can consider. Okay, and of course there is the requirement that the group structure on the Lie group becomes just matrix multiplication here in the set of matrices. So we have to require that if I look the matrix associated to the product of two group elements, that is the same as taking the matrix multiplication of the matrices of the individual group elements. So meaning that this combination going from G and H to the composition here now should really just correspond to taking two matrices and leading to a third matrix that is still in this kind of hypersurface. Okay. Now, given such matrices, we can really make sense of what this tangent space at the identity is by just taking, say, the derivatives of these matrices with respect to my parameterization of the Lie group. And the matrices that I find at first order, they are really the generators of my Lie group, x1 and x2, say, if my Lie group were two-dimensional. And I know that if I have some linear combination of these matrices, I can take the matrix exponential to get back to the matrices on the Lie group side. Now, the thing that I did not stress last time is that describing this as a representation going from the abstract Lie group to a collection of matrices, it really has an analogy on the Lie algebra side, where now before I had just an abstract vector space with different vectors and a Lie bracket, but I can also consider a representation on that side, which is just a mapping now from the Lie algebra to the n by n matrices. That should implement the structure of the Lie bracket now via not matrix multiplication, but the commutator. So if I have two generators here, I can now look at the commutator of those generators and saying that this is a representation of the abstract Lie algebra is really saying that if I take the image of the Lie bracket of two abstract vectors, say psi A, psi B, that is the same as taking the commutator of the image of psi A with the image of psi B. So here it's really the commutator, this additional structure on the Lie algebra. Okay. Now recall that we can encode the structure of the abstract Lie algebra in terms of the structure constant. So this is just saying that if I take my basis vectors psi A and psi B, that the Lie bracket of this is going to be a linear combination of these basis vectors again. And the coefficients are structure constants f, a, b, c, psi c, where of course there is a summation here of the index c. So now we can be more precise about what it means to have a representation on the Lie algebra side, or what it takes to construct such a representation. Well, what it takes is, well, we have to implement that the Lie bracket becomes a commutator on, say, the basis vectors. But we already know that there are these structure constants here. So if I label these images of the basis vectors by x1, x2, etc., then this is really requiring that these generators satisfy the same commutation relations as the abstract Lie algebra did. Okay? So as soon as we know the structure constants say of the Lie group G, then in order to find a n-dimensional representation of this Lie group and the Lie algebra, it is really sufficient to find a set of matrices that satisfies this relation. So determining an n-dimensional representation of G, or equivalently of the Lie algebra, is equivalent to specifying n by n matrices x1 up to xn, where little n is a dimension of the Lie group G, such that they satisfy this relation. So let me copy it again. XAXB is FABC XC. So as soon as I have such matrices, then I can look at arbitrary linear combinations of them, take the exponential mapping to get all the matrices that we have to assign to the abstract group element in order to get the representation on the Lie group side. So this is a very economic way of going about things, because now we really only have to specify a finite amount of data, just n explicit matrices that have to solve this equation. Okay? Now we want to classify representations of Lie groups, and as we've already seen for the finite groups, the way to go about this is not to classify all representations, but to start with the irreducible ones, because general representations can be built out of irreducible representations. So this decomposing of representations into irreducible ones, that holds equally well for Lie groups, at least when they're compact, like the ones that we're looking at. Okay, so let's recall what it means for a representation to be irreducible. So let's see. So recall. Representation from a Lie group to the invertible matrices is irreducible if it has no invariant subspaces, or I should more properly write no proper invariant subspaces. Proper invariant subspaces where, okay, so what was an invariant subspace again? Well, it was a subspace W, in this case of Cn, such that if I take any vector in W and look at all its images under all the matrices of the group, that they're again in W, so for all group elements. So this tells me when a representation on the Lie group side is irreducible, but one can equally specify this property on the Lie algebra side. So recalling that I can write G in general, or is it the representation of G as like the identity element plus linear combinations of the generators plus higher order terms. I mean, really requiring that every element of such a type is gonna preserve W in this linear subspace. Well, certainly the identity is going to do that. So also this first order term has to preserve this. So this is really equivalent to asking that for every vector in W, we want that the generator acting on this vector is also in W. So this is certainly a necessary condition, because by just looking at the elements that are very close to the identity. But now you can easily check that if I take an arbitrary exponential of a linear combination of these generators, that it will also preserve W just by doing the Taylor expansion. So this is really the condition that one would have to check in practice in order to make sure whether some subspace is an invariant subspace, and therefore we have to check that no such subspaces exist for a representation to be irreducible. Okay? So as I said, we're going to do this in an example which is really central to the classification of representations of all Lie groups. And this example is SU2. So in the exercises, you have already looked a bit at this Lie group. So let me briefly recall some things and give you a canonical representation of the generators, such that in the next part of this lecture we can really start classifying the representations. Okay, so recall SU2, that is the set of 2 by 2 complex matrices that are unitary and have determinant 1. And we've seen last week that the corresponding Lie algebra is the set of 2 by 2 complex matrices that are skew Hermitian, or anti-Hermitian if you like, and traceless. So the skew Hermitian part was really a consequence of the unitarity, and the tracelessness is really a consequence of the determinant of the group element being equal to 1. Okay, so these are skew Hermitian, and we're more used to actually working with Hermitian matrices, but note that we can get the Hermitian matrix just by multiplying this by I, right? So note that if I take I times x dagger, then I get a minus sign for the x dagger, but another minus sign from the I in front. So this is just I of x. So up to overall multiplication of all these matrices by I, I'm really looking at Hermitian traceless matrices. And these we've encountered a lot in other places. In particular, a basis of Hermitian traceless 2 by 2 matrices is given by the famous Pauli matrices. which are, let me write them down for completeness, sigma 1 and sigma 3 1 minus 1. And you can easily convince yourself that really this is a basis of the Hermitian traceless matrices. And in the exercises you have checked that they satisfy certain commutation relations, and we can use these to determine a nice set of basis generators of SU2. So we define x of a by convention to be minus I over 2 times sigma a. And this convention is chosen such that the structure constants take a nice form, namely, if I look at the commutator of xa of xb, it gives you exactly as structure constant the completely antisymmetric symbol epsilon abc. So recall, this is completely antisymmetric, and epsilon 1, 2, 3 is equal to 1. That specifies entirely this tensor. Okay? So what would be the goal of the remaining part of this lecture? Well, that will be to find different sets of matrices, so not necessarily two-dimensional like in this case, but any dimensional, so find m by m matrices x1, x2, x3 satisfying this relation, and that will automatically then furnish a representation of SU2. And of course we want to then check whether this representation is irreducible or not. So check irreducibility. Okay? So that we will do in the next video.